To our perfect classes. In this video, I will discuss important topics of database management system with practical problems which are important for BCA, BSCIT, MCA, BTECH, MTECH, UGC, GATE exams and any other exams of computer science and computer applications. Now I am going to start. First of all, I am going to discuss about database management system. These are the keys of database management system: candidate key, primary key, secondary key, unique key, composite key, surrogate key, partial key, foreign key, alternate key, super key. What is a key? First question arises in mind: what is key in database management system? A key is a set of attributes which can identify every row, tuple, row means tuple, uniquely in the given relation, or that is known as table. Means such a row, such a tuple which is uniquely identified in a table, in a relation, that is known as key. First, candidate key. Candidate key means a set of minimal attributes which can identify each tuple uniquely in the given relation is called as a candidate key, or you can say a minimal super key is called as a candidate key. It is possible to have multiple candidate keys in a relation. For example, we have given a relation A, B, C, D, E. In this relation, we have given functional dependency. A implies B, C implies D, D implies E. First step, we have to check on the right side what attributes are not given. Here we can see that A and C, these two attributes are not given. So AC, we can say that AC is a attribute of key. Now we have to find out closure of AC. If we find original relation again after closure of AC, then we can say that AC is a candidate key. AC closure. AC, you can see in question, A implies B, C implies D, D implies E. Means when you take AC closure, AC, A implies B, C implies D and D implies E. That means here we get again original relation. So that's why AC is a candidate key. The combination of essential attributes also known as prime attributes, is known as only possible candidate key. Prime attributes, essential attributes are the same. In this question, AC is a prime attribute, essential attributes, and non-prime attributes, non-essential attributes are B, D, E. Note, we should be keep in mind that if set of prime attributes cannot decide the remaining non-prime attributes, then set of prime attributes and some non-prime attributes will be candidate keys. Multiple candidate keys are possible. To find candidate key, we check different combination of prime and non-prime attributes. In next problem, we have given A, B, C, D, E a relation. C implies F, F implies A, EC implies D, A implies B. Which of the following is a key for R? Check on the right side what attributes are not given. You can check C and E attributes is not given. So that's why here we will be find C is closer. If after finding C is closer, we will find original relation again, then we can say that this is a candidate key. When we take C is closer, CE, C implies F, F implies A, and EC implies D. EC implies D and A implies B. Now you can check C is closer is original relation. So that's why C is a candidate key. In this question, prime attributes are CE, non-prime attributes are A, B, D, F. Now we have to find how many possible candidate keys and super keys are in this question. CK is only, candidate key is only one possible, that is EC. But super keys are possible. How can you calculate? You can calculate by this method. There are total 6 attributes. Now take the 6 blank lines. CE places on first 2 places and rest 4 places. Each place can contain 2 choices. Because here we see that in candidate key 2 attributes are taken for making candidate key. So that's why we can take in super key at least 2 choices. So remaining blank places are 4. Then 2 is multiply 4 times, we get 16. Now you can say that super key is possible on 16. So there are 16 ways of super keys. Now next question. In next question we have given A, B, C, D, E relation and functional dependencies are given. A, B, C depends C, implies C, B implies E, C implies D. And we have to determine total number of candidate keys and super keys. First of all, see on the right side what attributes are not given. Here you can see A, B. These are 2 attributes which are not given on right side. So we take here AB as a prime attributes and rest C, D, E are non-prime attributes, and take the closure of AB. AB to C and B to E and C to D. You can see we get again original relation. So that's why we can say that AB is a candidate key. Total possible candidate key is 1, that is AB. And in one candidate key there are 2 attributes. That means two places surely contained AB. And rest places are 3. And each 3 places each contain 2 choices. So that's why 2 multiply 3 times and we get 8. There are total number of candidate keys are 1 and total number of super keys are 8. In next question we have given relation E, F, G, H, I, J, K, L, M, N and set of functional dependency. E, F implies G, F implies IJ, K implies M, L implies N, E, H implies KL. What is the key for this relation? And these are the options are given. We have to find first of all on the right side what attributes are not given. You can see on the right side E, F and H, 3 attributes are not given. So first of all we have to find out closure of E, F, H. When we find closure of E, F, H, we find original relation again. So that's why we can say that E, F, H is a candidate key and E, F, H are prime attributes and non-prime attributes are G, I, J, K, L, M, N. Total possible keys, candidate key is only 1 possible and total number of super keys, you can find it 2 raised to power n formula. You can implement 2 raised to power n formula. When we implement 2 raised to power 7, you can get 128. This is your super keys. Now next question is, consider the relation A, B, C, D, E, H and set of functional dependency are given. D implies A implies B, C implies D, E implies C. What are the candidate keys of R? Right, on the right side you can see that EH is not given on right side, so that's why we have to find out EH's closure. But when we find EH closure, we find only EHC. So we can see EH closure is not possible. Now we will take some non-prime attributes with it. Check its closure is possible or not. We take here A with EH, B, EH, C, EH, D, EH. When we find AEH, we find original relation, BEH closure, then original relation. But CEH cannot give you regional relation. DEH also give you regional relation. So that's why we can say that here D option AEH, BEH, DEH. This is a candidate key. This answer is correct. And now next topic is, what is a functional dependency in database management system? In any relation, functional dependency, for example, alpha and beta holds. Alpha implies B. This is a functional dependency. If two tuples or rows having some same value of attributes, alpha also have same value for attribute B. If alpha and beta are two sets of attributes in a relational table R, where alpha subset or equal to R, but beta subset of alpha subset or equal to alpha, then we can say that functional dependency to exist from alpha to beta. Alpha implies beta. There are two types of functional dependency: trivial functional dependency, non-trivial functional dependency. A functional dependency X implies Y is said to be trivial if and only if when we say that Y subset equal to X, means Y should be subset of X. That is known as trivial functional dependency. If you can say AB implies A, AB implies B, you can say AB implies AB. This is a trivial functional dependency. Non-trivial functional dependency means a functional dependency X implies Y is said to be non-trivial if and only if when we say that Y is not subset of X. Y is not subset of X, that means non-trivial. That means AB implies BC, AB implies CD, but you cannot say that AB implies BCD in combine. What are the inference rules? What are the inference rules in database management system? First inference rule is additive, second reflexivity, third transitivity, fourth augmentation, fifth composition, sixth decomposition. Additive inference rule said if A implies B, if we say that A implies B and we say A implies C, then we can say that A implies BC. You can combine both B and C. Always holds. A always holds BC. If B is a subset of A, if we said B is a subset of A, then A implies B always hold. Transitivity means if A implies B and B implies C, then we can say that A implies C. Always hold. This is a transitivity. Augmentation means if we say that A implies B, then A C. If we add one attribute C that attribute will be added on the both side, left side and right side. Then we can say that AC implies BC always holds. Composition means if A implies B and C implies D, then AC implies BD always hold. Decomposition means if A implies BC, then you can say A implies B, A implies C. You can separate. That is always hold. This is an inference rule. Rules for functional dependency. Rule 1, Rule 2, Rule 3, Rule 4. In Rule 1, X implies Y will always hold if all values of X are unique and different irrespective of Y. Then we can say that X implies Y. And X implies Y will always hold if all the values of Y are same irrespective of Y. In Rule 1, these are unique. In Rule 2, these are same. And in Rule 3, for a functional dependency, X implies Y to hold if two tuples in the table agree on the value of attribute X, then they must also agree on the value of attribute Y. Means here we take the combination. And Rule 4, functional dependency, X implies Y violations will occur only when for two or more same values of X and corresponding value Y are different. Means for example, we can say that X implies Y. We take here 1, 2. We take here 1, 3. You can see here Y's value are different for same value 1. So this is a violation. Now example of Rule 1. Here you can see we have given a table. This is a table. Following functional dependency will always hold since all the values of attribute A. If we say that A implies B, means A holds B, then it is true because all values are unique of A and unique of B. If we say A implies BC, then also you can see all values are different on right side. So that's why true. A implies CD. A implies CD. Here you can see that 5, 8, 2, 4. 5's value 42, 8's value 42, 2's value 43, 4's value 43. Here left side are all values unique and on the right side value can be same. So that's why it's true. A implies BCD. BCD, it also true. A implies DE, it also true. A implies BCDE, it also true. A implies any combination of attributes A, B, C, D, E. Similarly, B and E. B and E also holds any combination of attributes A, B, C, D, E. But B, C and D do not hold. So we can say that these all are not hold. So functional dependency is not possible. You can see in the C. Here we have given C4. All values are same. And on the right side, all values are different. You cannot say one time 4's value 5, 4's, then another time 4's value 8, another time 4's value 2, another time 4's value 3. This is not possible functional dependency. This is not a functional dependency. When this type of situation is given, this is not possible of functional dependency. According to Rule 2, following functional dependency will always hold since all the values of attribute C are same. We can say if A implies C, AB implies C, AB, D, E implies C, DE implies C, AE implies C. We can say that functional dependency will always hold true because any combination of attributes that will be hold C, that will be functional dependency. Combination of rule 1 and 2, we can say that functional dependency alpha implies beta always holds if either all values of alpha are unique or if all values of beta are same. Means on the left side all values can be different, on the right side can be all values same. It is possible according to rule 2 for functional dependency. Now what is the equivalence of functional dependency? In database management system, two different sets of functional dependency for a given relation may or may not be equivalent. If A and B are two sets, for example, you have given two sets, 1, 2, 3. This is a one set and this is a second set, 1, 2, 3. Here you can see that all attributes are present in B and B's all attributes are present A. So we can say that both are equivalence. A covers B, A superset of superset and equal to B, and B superset of equal to A. You can say that B covers A covers B, and both A and B covers to each other, means A is equal to B. That is known as equivalence of functional dependency. And these are the some steps for determining whether A covers B or not. You can see these all are the steps. You can read it. Now next is a first question for checking equivalence of functional dependency. We have given relation A, C, D, E, H, which having two functional dependency, set A, set B. When we take set A, in set A, we have find out A's closure. We first of all we check the on the right side what attributes are not given. You can see here you can see here CAD H. You can see that E is not present, and on the right side you can also see in set B ACDH E is not present. Now A's closure is ACD. Closure of left side A, CD is using set B. You can see here when you take E's closure EHADC, closure of E implies AH, it also consider set B. When you calculate A's closure according to set B, you can also see A implies CD, it's according to set A. E's closure E implies AH, it also using set A. Comparison step 1, step 2. When you compare both are, you can see both are the same, and you can say functional dependency of set A can determine all the attributes which have been determined by functional dependency of set B. Thus we can say that A covers B and A superset is equal to B. And this is according to rule 1 and according to rule 2. When we find A's closure and AC's closure, we find ACD. Closure of left side A's implies C and closure of left side A implies D according to set A. You can also find out E's closure. When we find E's closure, you can see that E implies AD and E implies H using set A. Step 2, A closure, that is A implies C when use the set B. C is a closure, A, C, D. When you set B, AC implies D. E is a closure, that is E implies AD and E implies H according to set B. After that, you have to compare both and you can see B covers A and B superset is equal to A. And according to rule 3, option D is a correct. Now you can see what is a canonical cover in database management system. In database management system, a canonical cover is a simplified and reduced the version of the given set of functional dependency. You can say that it is reduced version. It is also known as irreducible set. Means in canonical cover you can find that attribute which is not written, then your relation is complete without it. And it is free from all externals. Functional dependency. The closure of it is same as that of given set of functional dependency. And it's not unique and it may be more than one for given set of functional dependencies. Why we need canonical cover in database management system? Why we use why we need canonical, why we require canonical cover in database management system? When we working with this set containing external functional dependency, it increases the computational time and its need to reduce by eliminating useless functional dependency, and this reduces the calculation time and working with the irreducible set becomes easier. For calculating canonical cover, there are following steps we should follow. First step we should first of all write the given set of functional dependency in such a way exactly one attribute on its right side. For example, we have given x implies yz. We have to write it as x implies y, x implies z. Now, step number 2. Each functional dependency one by one from this set obtained in step 1. Now, third step. Determine whether it is essential or non-essential by computing closure of its left side. Then find the particular dependency is present in set, particular functional dependency is not present in the set. There are following two cases are possible. Case 1, case 2. In case 1, if results come out to be same, it means presence or absence of the functional dependency does not create any difference. But if results come out to be different, that means presence or absence of functional dependency created differences. If it is non-essential, non-prime attribute, if it is a non-essential, non-prime attribute in case 1, in case 2, it is essential prime attribute. In case 1, it eliminates the functional dependency from the set. You can eliminate it. But in case 2, don't eliminate that functional dependency from the set and mark the functional dependency as essential. And step 4. Now take the newly obtained set of functional dependency after performing step 3. Check if there is any functional dependency that contain more than one attribute on its left side. The following two cases will be possible. In case 1, there exists no functional dependency containing more than one attribute on its left side. In this case, the set obtained in the step 2 and 3 is the canonical cover. In case 2, there exists at least one functional dependency which containing more than one attribute on its left side. In this case, consider all such functional dependency one by one and check if their left side can be reduced or not. And in short, we can say that first of all, consider functional dependency, then calculate closures, then check the subsets can we produce same result or not. Then after that step is complete and the set obtained is canonical cover. For example, we have given one relation that is R W X Y Z. X implies W, WZ implies XY, Y implies the WXZ. Now you have to, first step is you have to write right side separately on a single attribute. X implies W, WZ implies X, WZ implies Y, Y implies W, Y implies X, Y implies Z. Now you can find closure of X. When we find closure of X, we find that X implies W or X implies X. Here we ignore X implies W because X closure is X. X implies W is essential and cannot be removed. WZ implies X. When we find its closure, we find WXYZ. It's non-essential and can be eliminated because WZ implies Y. From WZ Z closure WZ and WZ2 implies we find the closure WZYZ, and it is essential and cannot be eliminated. Y implies W, Y's closure is Y, W, X, Y, XZ. It is non-essential and can be eliminated. Y implies X, Y implies when we find Y's closure Y, X, W, Z and Y's closure Y, Z. It is essential, cannot be eliminated. Y's implies Z, W, X, Y, Z and W, X, Y. You can see it is essential and cannot be eliminated. Our essential functional dependencies are X implies W, WZ implies Y, Y implies X, Y implies Z. Now you reduce left side if it contains more than one attributes. WZ implies contain more than one attributes on the left side. You can find the WZ's closure. WZ, XY. Now consider all the possible subsets of WZ and find the closure of Z. W and Z. W's closure W, Z's closure Z. We can conclude that we can write WZ implies Y, W implies Y, Z implies Y. Finally, the canonical cover is X implies W, WZ implies Y, Y implies X, Y implies Z, and this is a canonical cover. Thank you. If you like my video, please like and share my channel for next coming videos. In next videos, I will discuss next part of database management system, which is related to decomposition of relations, lossless decomposition, dependency preservations, types of decompositions, rules for decompositions, and normal forms, how normalization in database management system. All these concepts will be discussed in next videos. What are different types of keys in database management system?